Hey everybody, this is our lesson on radioactive decay. And by the end of this lesson, you should be able to compare nuclear reactions, including alpha decay, beta decay, and gamma. So, first off, let's just define what radioactivity is. And this is the process where an unstable nucleus emits a charged particle of a certain type and energy as it decays. Any atom containing an unstable nucleus is called a radioactive isotope or radioisotope, which is how we'll refer to it from now on. And during this type of decay, atoms of one element will change into atoms of a different element altogether. So instead of looking at electrons here, which is what we tend to see changing, we're actually looking at proton number changing. So nuclear radiation, again, are charged particles and energy that are emitted from radioisotopes, specifically from the nucleus. And that tells you right there that we're dealing with either neutrons or protons because electrons are not in the nucleus. And then there are three common types of radiation that we'll look at in this lesson, and that's alpha, beta, and gamma radiation. So first, let's look at alpha decay. And alpha decay is a positively charged particle, and it's made up of two neutrons and I don't know why it doesn't have this on there, and two protons, so it actually looks like a helium nucleus. This usually refers to the nuclear decay that releases alpha particles, which is a nuclear decay reaction. And in alpha decay, the product isotope is two less protons and two less neutrons than the parent isotope. So the product is also referred to as the daughter. The reactant isotope is referred to as the parent here. So it is a mass of 4 less and an atomic number of 2 less. These are the least penetrating type of nuclear radiation, so these are the weakest form. They can be stopped by a sheet of paper or even your clothing, so they wouldn't even break the skin on a human. And so this is what alpha particles look like. Alpha decay, as you can tell, looks like this helium atom over here. And this is uranium breaking down into thorium and the alpha radiation. The next type is beta decay. And this is when an electron is emitted from an unstable nucleus. So the way to think about this is a neutron, which we know is neutral, is made up of a proton and an electron hooked together. So since it's a positive and negative hooked together, they cancel out, making them neutral. Well, here what happens is one of those neutrons will emit an electron off. And since it's emitted an electron, that original neutron has become a proton. So because of its negative charge, a beta particle is assigned an atomic number of -1, since it's an electron. And during this type of decay, a neutron decomposes into a proton and electron, where that electron is then emitted from the nucleus. The product isotope, or the daughter isotope here, is going to be 1 proton more than the parent isotope, and it's also going to be 1 neutron less. So it's going to weigh a little bit lighter, but it's going to be 1 element down on the periodic table, or over on the periodic table. And then beta particles are more penetrating than alpha because they are smaller, so they move a little bit faster. I like to compare alpha particles to like getting hit by a wiffle ball. Like, it's not really going to hurt that bad. And then I say that beta particles are more like a BB. So if you get hit by one of those, it's going to hurt. And these tend to be stopped by thin sheets of metal, so they're still not super strong, but stronger than alpha. And here is a beta decay reaction. So we've got thorium, which then loses, you can tell, loses an electron, and this dot was white as a neutron, becomes blue as a proton, and it's ejected that electron out. And then our last type here is gamma radiation. And this is a ray. So we actually don't even call this a gamma particle. We call this a gamma ray. So it's actually a wave of energy that's emitted from the nucleus. It has no mass and no charge, so its symbol is actually this little Y that you'll see in a minute with a 0 up top and a 0 on the bottom. So also you can tell we note these types of decay with their isotope notation. So they've got the mass number up top and the atomic number at the bottom. So make sure to remember that. And then these will travel through space at the speed of light. So it is just an energy ray. And the atomic number and mass number of an atom will stay the same, but the energy of the nucleus decreases because it has been emitted. A lot of times gamma radiation actually just accompanies one of the other two so that you can see some sort of change to the nucleus, because you can't really see an energy change, right? But you can see a mass change or an atomic number change, which is why it tends to accompany alpha or beta. And then these are much more penetrating than either alpha or beta. These are just, it's pure energy, so they have much more penetrating power, which is why they can only be slowed down really by lead and concrete. Pretty sure it's 6 feet of lead and 10 feet of concrete that can slow gamma down. It still doesn't even stop it completely. So here is what gamma radiation looks like, and that's, like I said, the symbol for radiation for gamma. So now that we know those three, let's talk a little bit about background radiation. And this is radiation that occurs naturally in the environment. So this is something that just is given off in our surroundings. This can ionize atoms. So it can turn them into ions by changing that electron count or that proton count. And the devices that are used to detect this are Geiger counters. And they have like badges that they look at, and they tend to have a meter that will go off as radiation is present. And here's just a video showing you, like a little cartoon showing you how a Geiger counter would work.